Alrighty, all time for the last video, chapter 13. So in this video, we're gonna talk exclusively about finding absolute extrema, which is another way of saying that we're basically doing optimization problems, absolute maxima, absolute minima, right? And we're gonna look at a couple of different methods of doing that. So to start off with, when you were a Cal 1 student, you learned about finding absolute extrema on an interval by basically looking for critical points and endpoints. The idea is you would plug critical points and endpoints into your function. Highest y was the max, lowest y was the min. Key thing here is that this only worked, like we were only guaranteed to have an absolute max and an absolute min if our function f of x is continuous in between and at the endpoints, right? So when we look at functions of two variables or more, right? Think of it this way. Rather than having a set line of x values that we're looking at, we actually have a two-dimensional boundary that we analyze our function on. So in this case, let's say that I have a boundary that's a rectangle. Basically, all the x's have to be between a number and a number, and all the y's have to be between a number and a number. So let's say that this is my boundary region. Well, remember, functions of two variables have graphs that are three-dimensional surfaces. So let's say, for the sake of simplicity, that I have basically a paraboloid, and this could work pretty much with any three-dimensional shape. So paraboloid, remember, looks something like this. What I like to call the bed sheet ghost costume. Yeah. All right. But anyway, essentially, this rectangle, like we have values of x and y that are going to go beyond what's in this rectangle. This rectangle, if I were to trace it out to points that are on uh, the paraboloid, I would end up getting essentially like an outline, right? Like, so all the x and y points that are in this rectangle, I would trace up to where the surface is. That would get me kind of like a two-dimensional outline. Think of it as I'm cutting the three-dimensional shape along this outline. That doesn't have to be like a straight circle. It could be like ridgy and weird. But the point is I'm cutting along a two-dimensional line, right? And what's going to happen is I'll be able to detach a part of that three-dimensional surface, and I'll have like a little 3D printed wonky potato chip or something, right? And essentially, we want to find what the highest and lowest points are on that wonky potato chip. So let's look at an example involving a function with two variables. So we have f of xy is equal to x squared plus 4y squared minus 2x squared y plus 4. And we want to find the absolute max and min of f bounded by the rectangle. That's not how you spell rectangle. Yeah. Where the x's are all between -1 and 1, and the y's are all between -1 and 1. So it really makes a square, right? So now that we have all of our stuff, remember, we essentially want to test f of x, y at any critical points and at boundary points. So that works essentially by doing a couple of things. First, figuring out where the critical values are. which means we need to look at our domain. We need to set our gradient equal to 0 and figure out critical points from there. Other than that, rather than having just one single boundary point that we plug in and analyze, we have boundary edges because we're looking at essentially a rectangle instead of just a straight line. So with that in mind, yeah. So with that in mind, we'll start off with the simple case. First off, if I look at x and y, all the terms in my function, there are no math no-nos that can happen. I can plug anything in for x, anything in for y, and I will get a value for f. So with that said, I'm only going to get my critical values from setting my gradient equal to the 0 vector. All right, so my gradient is equal to, right, differentiating with respect to x, I get 2x, 0, minus 4xy, and 0. Differentiating with respect to y, I get 0, 8y, 2x squared, and 0. So now I've got my gradient. If I set each component of my gradient equal to 0, I get a system of equations to solve. So like before, I'm going to try to substitute. I'm going to get y by itself in this equation because it's going to result in something that's easier to work with than solving this for anything. Right? Which wouldn't be bad, but yeah, path of least resistance here. So if I solve for y, I'm going to add 2x squared to both sides. I get y equals 2x squared over 8, which is the same thing as x squared over 4. Now that I have something to substitute y with, I'm going to go back to my other equation, and wherever I see y, I'll replace it with x squared over 4. So we get 2x minus 4x times x squared over 4. All right, my 4's will divide, and I'll be left with 2x minus x to the third equal to 0. At this point, I notice that I have yeah. At this point, I notice that I have a factor of x in both terms, so I can factor that out. And I get two possibilities. X is equal to 0, and x is equal to plus or minus the square root of 2. So this is where these boundaries are going to help us a lot, because this would mean that I have 3 different values of x to figure out my y for, and I mean, not bad, but still. Remember, x has to be between -1 and 1. The square root of 2 is greater than 1 because 1 is the square root of 1. So neither of these will actually fit in that rectangle, right? The x coordinates that we just got there would be like out here. So we're not concerned with those. Don't need them. These are outside the rectangle. We only need to worry about x equals 0. So if x is equal to 0, we can go back to our equation for y and figure out that y is 0 squared over 4, also known as 0. So the critical point that we got, and we only have one that we need to consider, is 0, 0. So we have one critical point, 0, 0. Now, the other parts are going to involve those boundary edges that I talked about. So for boundary edges, essentially, I'm going to plug the endpoints for each of the variables into my original equation, right? So these were my boundaries to remind you. All right, so if I start off by keeping x constant, I can have x equals -1 and y equals anything. So if I plug -1 in for the x's to my original equation, I end up getting -1 squared +1 plus 4y squared minus 2 times negative 1 squared times y. In other words, minus 2y plus 4. So combining like terms, I get 4y squared minus 2y plus 5. Now, if you look at this, by keeping x equal to one of its boundary values, I essentially just have a function of one variable. So I can figure out if there's a critical value to assess, right, when x is held constant at -1. Right, this would be like the edge of the potato chip doing like a whoop-de-woo, right? And I can do that the same way that we did in Cal 1 by taking the derivative, setting it equal to 0, and solving. So derivative of 4y squared, we get 8y. Derivative of minus 2y minus 2. Derivative of 5, 0. Set this equal to 0, and I get y is equal to 1/4. So from that, my next point I need to check is -1, 1/4. Now, thing I want you to consider before I talk about the next thing is that in the original function f of xy, all of the x's are squared. When all of your x's are raised to an even power, f of -1 will give you the same thing as f of 1. So the next thing I had to check was f of 1y, right? That's keeping the x constant at its other boundary value. But because all the x's in the original are squared, this is going to result in the exact same thing, right? 4y squared, minus 2y plus 5. And if I do the same analysis, I'm going to end up with the same point, except with a positive one for the x. And remember, what am I going to do with these? I'm going to plug them back into the original function. And when I do that, it doesn't matter if the one is positive or negative because all the x's are squared. So I'm going to save myself a little bit of work here by recognizing that property of squared numbers. If that's not something you were able to catch, then you can just go ahead and do the exact same thing you did, and you'd get the point 1, 1/4. Okay, and this is what it looks like when we fix x to its boundary values. Now we'll look at what happens if we keep y fixed to each of its boundary values. So f of x -1, okay, I'm going to get from substituting -1 for every y in the original equation. So I get x squared plus 4 times -1 squared, so plus 4, minus 2x squared times -1, which will become plus 2x squared, and plus 4. If I combine like terms, this will become 3x squared plus 8. Now, if I do my analysis, I'll take my derivative, 6x, and then that's 0, equals 0. If I solve that for x, I end up getting x is equal to 0, which means that a critical point I get from this edge is 0, -1. Now for this one, technically not all of the y's are going to be squared, right? There's just a regular y right here. So we would end up getting a different function for f of x and 1. Right, but in this case, let's see what happens. So we get x squared plus 4 minus 2x squared plus 4. Combining my like terms, I get -x squared plus 8. If I take the derivative, I get -2x equals 0, which means that x equals 0. So I end up also getting the point 0, +1. And now I have all the points that I need to go through and figure out my absolute extrema. So we'll start off with our critical value, 0, 0. So if I go back to my original, which I will write here for for convenience, all right, when I plug 0 in for both x and y, all of these terms will zero out except for the 4. So f of 0, 0 is 4. if I use my next point, which I can write plus or minus 1/4, because I will get the same z coordinate since all the x's are squared. So it's okay for me to do that for this one, not for these two though. Right. I end up getting 1 plus 4 times a fourth squared. I'll just write that here. Minus 2 times 1 times 1/4. All right, positive or negative 1 squared will just give me 1, so I'm only writing 1. Plus 4. Okay, doing a little arithmetic. This would be 1/16. If I multiply that by 4, this becomes just 4/16, also known as 1/4. If I multiply these guys together, 2 times a fourth gives me 1/2. If I take 1/4 minus 1/2, that gives me negative 1/4. So 5 minus 1/4 gives me 19/4. And if I wanted to write that as a decimal, that would be 4 3/4 or 4.75. Next, we have f of 0, -1. Okay. In this case, it actually does end up getting the same z coordinate for both of these points, but that's only because the x is 0. Because the only point where the sign for the y coordinate would matter has a factor of x squared, and if that's 0, that whole term is 0. So we're actually going to get the same thing for both of these. I'm not combining them though, because if I had any other value of x besides 0, I would get different z coordinates for these guys. Whereas with this one, all the x's were squared, so it didn't matter, right? So anyway, if I plug these numbers in, 0, that's going to be 4, that's going to be 0, that's going to be 4. 4 and 4, I get 8. So now I have all of my z coordinates calculated. The highest z coordinate is my max, the lowest z coordinate is my min. So I have an absolute maximum value of 8, and this occurs at the coordinate 0, positive or -1, 8. If I look for my absolute minimum, that's going to have a value of 4, and this will occur at the coordinate 0, 0, 4. So one thing I want to point out here is functions of two variables have graphs that are three-dimensional surfaces. So two independent variables, it will give you a three-dimensional graph. So when I got these points and I wrote down like 0, -1, that's the equivalent of doing a one variable problem and just saying x equals, right? Because x is an input. Here, x and y are both inputs. So having just this is not the actual coordinate on the graph, right? This just tells you where you are on the floor. You still have to figure out the z coordinate, right? But these are the actual points on the graph of the three-dimensional surface. Okay, so now that I've clarified that a bit, on to the next example. So the thing about that is we had a very simple boundary there, and it wasn't hard. It wasn't very hard for us to plug numbers in for x or y to figure out boundary points. But rectangles are not the only kinds of boundaries we can have when we're looking at functions of two variables. We can have any two-dimensional shape be the boundary. And when you try to do like hyperbolic boundaries with something like that, that gets very nasty. So luckily for us, there's a bright young lad who is only 19 years old, whose last name was Lagrange, that you might remember from Cal 2 with the Lagrange error bound. Yeah, same guy. So when he was 19, he came up with a concept called Lagrange multipliers. Basically, what this did is it took into account the boundaries by introducing a third number called the Lagrange multiplier and made it so that we actually could solve for all of the points that need testing to find absolute max and min without having to do separate things to take boundary points into account. So the process for finding Lagrange multipliers already involves us using the boundary. So we don't have to do any extra work after solving for critical points. We don't actually even have to solve for that. All of it will be taken into account when we solve for the Lagrange multipliers. Definitely not what I was doing when I was 19. But anyway, so Lagrange multipliers, essentially, if I want to find the absolute max and min of f bounded by some two-dimensional boundary G, right? I can solve this equation. The gradient of f is equal to lambda, Greek letter, times the gradient of G. So again, G is the boundary. So like in the last example, that would be a rectangle. F is the function whose max and min we're trying to find. Lambda is what we call a Lagrange, love writing that in cursive, multiplier. All right, so this lambda is a Lagrange multiplier. I like to think of it as like a middleman that kind of takes away some of the workload from us working the problem. Kind of nice. Most middlemen aren't that useful. Oh, whoops, did I say that? Anyway, um, now that we got that equation written out, let's see it in action. So for an example, let's say that we want to find the absolute max and min of this function, f of xy equals 5x minus 3y, bounded by x squared plus y squared equals 136. So basically we have this three-dimensional surface. The bound is actually going to be a cylinder, right? And well, no, a circle. Yep. So we're in two variables, not three. So our floor area, we would basically be drawing a circle, right? With salt. Ooh, no. Basically, this is a circle that has a radius of the square root of 136, which is going to be 11 point something. Yeah, it's not totally important, but basically we're going to have this surface. It can look like any kind of wackadoodle surface, right? If I were to trace points up from that circle that I drew on the floor to the three-dimensional surface, right? I would basically get some kind of a line on my surface. If I like laser cut this and pull it off the top, I get that weird potato chip that I was talking about earlier. And again, we want to find the maximum and the minimum values. So the highest and lowest point on the weird potato chip. So with that said, let's set up our equation. We know that delta, or not delta, del, gradient of f is equal to lambda Lagrange multiplier times the gradient of g, where g is the boundary equation. So technically, you would want everything on one side, and that serves as your g, right? But because 136 is the only thing on this side and it's a constant, I'm not going to worry about it. I'm just going to use x squared plus y squared. Because if I were to take the grade or the derivative of this with respect to any variable, it would be zero. So I'm not going to lose sleep over it. Now, that said, gradient of f. So going back to this function whose extrema we're trying to find. Derivative with respect to x, I get 5. So 5i. Derivative with respect to y, I get -3, so minus 3j equals lambda times gradient of g. So if I take the derivative with respect to x, I get 2x. That'll be 0. That'll be 0. So 2x. But I'm multiplying that by lambda, so 2 lambda x. Derivative with respect to y, I get 0, 2y, and minus 0. So 2y multiplied by lambda. Every time I write a 2, I end up writing a lambda. It's the strangest thing. So 2 lambda yj. All right, so now that I've got this set up, remember if two vectors are equal, that means that their components are equal to each other. So I get a system of equations by setting the I components equal and the j components equal. Okay, so here's what we're going to do now. I'm going to solve each equation for the variable that's in it. So top equation, I'm going to solve for x. I get x is equal to 5 over 2 lambda. Bottom equation, I'm going to solve for y. I get y is equal to -3 over 2 lambda. And at this point, I have something I can replace x and y with, and this is where we take the boundary into account so that we don't have to do the extra work later. Right? Essentially, I'm going to take my boundary equation, the whole thing, and wherever I see x, I'm going to replace with 5 over 2 lambda. Wherever I see y, I'm going to replace with -3 over 2 lambda. So I end up getting 5 over 2 lambda squared plus -3 over 2 lambda squared is equal to 136. Now, when I square these terms, remember a square fraction, you square the top and the bottom. I get 25 over 4 lambda squared plus 9 over 4 lambda squared equals 136. Since these already have the same denominator, I can combine these and write it as one fraction. 34 over 4 lambda squared equals 136. Now doing a little bit of algebra, I can multiply both sides by this denominator, divide both sides by this guy, and I end up getting 4 lambda squared is equal to 34 divided by 136. And in case you didn't know, 136 is just 34 times 4. So the right-hand side actually just reduces to 1/4. So if I want to solve for lambda, divide both sides by 4, I get lambda squared is 1 over 16. Take the square root of both sides, I get lambda is plus or minus 1/4. So now I have two possible values for lambda. And what's going to happen is this is going to result in me getting two possible points where I'll have an absolute max or min. So with that said, let's figure out what those points are going to be by using these equations that we came up with a second ago. So we'll first consider the case where lambda is -1/4. When that happens, I get that x is equal to 5 over 2 times -1/4. That'll be -1/2, which results in an x value of -10. I also get y is equal to -3 over 2 times -1/4. Right? Doing a little bit of arithmetic, this will end up being +6. So collectively, when I use -1/4 as my Lagrange multiplier, the result is the coordinate -10, 6. Remember, that's an input coordinate. We still have the z coordinate if we want to say where on the surface we are. So this is one point that we're going to have to test. To get the other, we're going to take lambda equal to +1/4. When I do that, I get x is equal to 5 over 2 times +1/4. That's going to end up giving me +10. And I get y is equal to -3 over 2 times 1/4, which will end up giving me -6. So collectively, when I use positive 1/4 as my Lagrange multiplier, I get 10 -6 as my input. So now that I know the two places, the two XY coordinates where I could have a max or a min, I'm going to plug both of those in to my original function. Remember, highest Z coordinate is my max, lowest Z coordinate is my min. So starting off with -10, 6. I'm going to have 5 times the X coordinate minus 3 times the Y coordinate. So -50 minus 18 gives me -68. Now doing the other one, 10 -6. We have 5 times the X coordinate minus 3 times the Y coordinate. So that's going to be 50 plus 18, which gives me +68. Almost nice. All right. So at this point, I have both of those values. These are my Z coordinates. This is the low one, so that's my absolute minimum. This is the high one, so that's my absolute maximum. So again, for clarity's sake, we'll say that the absolute minimum value of Z would be equal to -68, and this will occur at the coordinate -10, 6, -68. So this is the exact location on the three-dimensional surface where we have that absolute minimum. So that's the exact coordinate on the wonky potato chip. Now the absolute maximum value is equal to +68. That's the Z coordinate that we just calculated. And this occurs at the coordinate +10, -6, +68. So again, this is the point on the potato chip where we have the absolute maximum. Right, and that's all we had to do. So you see, we didn't really have to do anything quite as involved as we did with that rectangle problem, right? The critical points and the boundary are all taken into account by solving that equation, which is a really powerful tool for us to have. Still a little bit salty that he did that at 19. All right, so let's go on to another example. So now we'll look at how we can use Lagrange multipliers to find extrema on a four-dimensional graph, right? So we don't even have visuals for this stuff, right? But based on what we know about functions of two variables and how we were able to extend from one to two variables, we can apply similar logic, actually the exact same logic, to functions of three variables. So let's say that I have f of x, y, and z equal to xyz. Let's say that we are bounded, this is another example, by the plane x plus y plus z is equal to 1. And we're going to constrain this even further to say that x, y, and z are all non-negative, greater than or equal to 0. So first thing I'm going to do is write out my equation for the Lagrange error bounds. So we have gradient of f is equal to lambda times the gradient of g. In this case, g will be x plus y plus z. I could subtract the 1 if I really want to, but when I differentiate, that'll go away no matter what. So gradient for f. If I differentiate with respect to x, remember this is x times a number, so the derivative will just be the number, yz. So yzi with respect to y is the variable. If I take its derivative, we just get the number xc. And finally, xyk. Now we'll move on to this. So if I take the derivative of x plus y plus z, with respect to x, I'll get 1 for that term and 0 for the others. So 1 multiplied by lambda, I get lambda I. Derivative with respect to y, 0, 1, 0. Times lambda, I get lambda j. And then similar thing with z, right? 0, 0, 1. Multiply by lambda, I get lambda k. So now I have the equation that I need to solve for my Lagrange multiplier. And I'll need to solve a system of 3 equations this time. So we get yz is equal to lambda, which I got from setting the I components equal. Then I get xz is equal to lambda, which I got from setting the j components equal. And xy equals lambda, which I got from setting the k components equal. So this one's going to be a little bit trickier, right? So I'm going to start off by solving 2 of these equations for the same variable. Well, actually different variables. All right, so let's say that I solve the first equation for y. I get y is equal to, actually, let's not do that one. Match what I did earlier here. So I noticed that both of these equations have x, right? So I could solve both of these equations for y and for z and get something that involves x that I could then plug into the third equation. That's not the only way that I can do it. If I wanted to, I could solve these 2 equations, one for x, one for y, and then plug them both into this one, right? But the point is, if I solve 2 of these equations, then I can substitute the result into the third equation. That's what we're going to do here. So I'm going to start off by solving both of these to something in terms of x. So I get z is equal to lambda over x. From this one, I end up getting y is also equal to lambda over x. Now I can take what I got there and substitute the y and the z both with lambda over x. So that's going to be lambda over x times lambda over x is equal to lambda. Multiplying these together, I get lambda squared divided by x squared equals lambda. And at this point, I can clear the fraction by multiplying both of these terms by x squared. So caveat here is that for this to work out, I'm only going to get solutions that have a non-zero x coordinate. So with that said, I end up getting lambda squared is equal to lambda x squared. So I know you're thinking, hey, why don't I just divide by lambda? Don't do that. Because if you do that, what's going to happen is you're going to end up missing out on one of the solutions we get for lambda. So I'm going to subtract lambda x squared from both sides. And we get lambda squared minus lambda x squared is equal to 0. Now, if you look, both of these have a factor of lambda. So I can factor that out. I'm leaving behind lambda minus x squared. So I get 2 solutions from this. I get lambda equals 0. This is the one you would have missed out on if you had divided by lambda. And I get lambda is equal to x squared, which I got from adding x squared to both sides. So now that I've solved for those possible values of lambda, what's going on over there? Oof. All right, I can go back to my constraint that I had to figure out the points that I can test. So you have 2 possibilities. One is that lambda is equal to 0. If that's the case, then my boundary equation is going to be x which I'm going to write as x because I never actually solved for x in terms of lambda, which is a weird thing that happens with these systems of three equations. Sometimes, yeah. Plus y, which I do know in terms of lambda. So that was lambda over x, plus z, which I also know in terms of lambda, lambda over x. And this is all equal to 1. Thing is, if I'm letting lambda be equal to 0, then that's 0 over something, which is 0. This is 0 over something, which is 0. So I end up getting x is equal to 1, and everything else is equal to 0. So when lambda is 0, the coordinate that I get is 1, 0, 0. And again, that's an input. That's like saying x equals if you're in one variable. So that's one thing I have to test. The other thing I'll get from letting lambda equal x squared. And again, x is going to be x. I can't do anything about that. Y is going to be lambda over x. Z is going to be lambda over x. And this is equal to 1. So first off, I'm going to explicitly write out what y and z are here. So y would be equal to x squared over x. Actually, we'll save that for later. Yeah. Save that one. Yeah. But anyway, lambda is x squared. So I'm going to replace all of these lambdas with x squareds. Okay. And again, keeping the caveat that x cannot be 0 for these solutions. We end up getting x plus x plus x, also known as 3x. So if I solve for x there, I end up getting x is equal to 1/3. Now I can actually write out what I was saying earlier. Y was equal to x squared over x, also known as x, also known as 1/3. Z is going to be the same thing. It's x squared over x, also known as x, also known as 1/3. So the other point that I have to test is 1/3, 1/3, 1/3. So those are the two coordinates that I need to input to find my max and my min. So if I start with the top one, f of 1, 0, 0, remember we're plugging into our original x, y, z. So this is going to be 1 times 0 times 0, which is 0. Second one, we have f of 1/3, 1/3, 1/3. So that will be 1/3 times itself, which gives me 1 over 27. So 1 over 27 is my absolute maximum value, which will occur at the point 1/3, 1/3, 1/3, 1/27. Remember, that's your W coordinate, your fourth coordinate. And then 0 is our absolute minimum value, which will occur at the coordinate 1, 0, 0, 0. So this is a W coordinate. And there we go. We've used Lagrange multipliers to find absolute max and min of a function of 3 variables. We are so fancy. Okay, and now shift gears a little bit to something that is also pretty powerful. So up until now, we've used Lagrange multipliers to find max and min when we're only given one boundary. The reality is we could actually use Lagrange multipliers to find maxes and mins when we have multiple constraints put on the function. And when you're trying to narrow something down to a specific point somewhere, like if I'm in the wilderness with thousands of square miles of mountains and hills, I can pinpoint something exactly the more constraints I have. So with that said, we'll look at an example where we're finding our max and min, right, with two constraints. Once you see how this extends into two constraints, then you'll be able to extrapolate to as many constraints as you want. So our function is f of x, y, z. So this is another function of three variables equal to 4y minus 2z. So we want to find the absolute max and min of this guy, okay, bounded by two things. We're bounded by a plane at 2x minus y minus z equals 2, and we are bounded by a cylinder, x squared plus y squared equals 1. So with that said, we have two different bounds. So the equation that we use to solve for our Lagrange multiplier will now include two Lagrange multipliers. One of them will still use lambda, right? And for the first one, we'll look at the plane. We'll let this be our g. So lambda times the gradient of g plus the second Lagrange multiplier that will correspond to the second boundary. And this one will use a different Greek letter. The next one after lambda would be mu. All right, so plus mu times the gradient of h, and h is going to be the boundary equation for the second bound. Okay. So the extension here is if I have more than two, I can just keep adding on, right? Plus multiplier times gradient of next one, plus multiplier times gradient of next one, and so on and so forth. So this is what 2 looks like, but it's very, very similar for anything more than that. Now, that said, my gradient for f, if I take the derivative with respect to x, the whole thing is 0 because there's not a single x in that equation. So no I component. Derivative with respect to y is 4. And derivative with respect to z is -2. Okay. So now we're going to have lambda multiplied by the gradient of g. So derivative with respect to x is 2. With respect to y is -1. With respect to z is also -1. Plus mu times the gradient of h. Derivative with respect to x is 2x. Derivative with respect to y is 2y. And there is no z, so that will be 0. This will not have a k component. So multiplying, I would get 2 lambda, negative lambda, negative lambda, 2 mu x, 2 mu y. The other thing to consider here, though, is that I have to combine x components, y components, and z components. Well, I shouldn't say x, y, and z. I should say I, j, and k. So combining together all of my I components, I'm going to get 2 lambda plus 2 mu x. Combining together all of my j components, I get negative lambda plus 2 mu y. So I'll write it as 2 mu y minus lambda. And then for my k component, I just have negative lambda, and there was no k here, so minus lambda k. And then from this point, I can get my system of three equations by setting the I components equal, the j components equal, and the k components equal. So for the first equation, there was no I over here. So we have 0 equals 2 lambda plus 2 mu x. Second equation, we get 4 is equal to 2 mu y minus lambda. And then for the third equation, we get -2 equals negative lambda. Well, that is super convenient because if I divide by -1 on both sides, I get lambda is equal to 2. Look at that, I have one of my multipliers. So now that I know that, I can substitute the 2 anywhere that I have a lambda on these sides. So first thing, I would end up getting 2 times 2, 4. So 0 equals 4 plus 2 mu x. And then over here, we would get 4 equals 2 mu y minus 2. Now, at this point, we're going to do what we did in that first example. We're going to solve for x and y in terms of the Lagrange multiplier mu. So if I take this equation and I solve for x, I would start by subtracting 4. Then I would divide by 2 mu. If I simplify that, I end up getting negative 2 over mu, and that's my x. Remember, we're going to take this and we're going to plug into one of these boundary equations. It'll be pretty obvious which one when we're done. Then for the y equation, I'm going to start by adding 2. I get 6 and dividing by 2 mu. And if I simplify that, that gives me 3 over mu, which is y. So now I don't have anything about z in terms of anything. So I'm going to use the boundary equation that doesn't involve z. That's going to be the cylinder, x squared plus y squared is 1. So if I rewrite that, x squared, we're going to replace with negative 2 over mu squared plus y, that'll be 3 over mu squared is equal to 1. So doing a little arithmetic, we get 4 over mu squared plus 9 over mu squared. Since they're both over mu squared, I can add the 4 and the 9, and I get 13 over mu squared equal to 1. Multiply both sides by mu squared, I get 13 is equal to mu squared. Take the square root of both sides, and I have two possibilities. Mu is equal to positive square root 13, or mu is equal to negative square root of 13. So with that in mind, I can look at these two possibilities and I can go back to my other boundary, right, my other boundary equation, which I can then use to figure out what z would have to equal. So start off with the case where mu is equal to negative square root of 13. When this happens, who is that? I don't know who that is. A long. Nope, go away. All right. So anyway, if I let mu be equal to negative square root of 13, then x is going to be negative 2 over square root 13. No further simplification required. Y is going to be positive 3 over the square root of 13. Actually, my signs are switched. X will be positive because we're dividing a negative by a negative, and y will be negative. Okay. So now I have values for x and y. If I go back and use my other boundary equation, right? So this one here, the plane, I can solve for the value of z. So I have 2x minus y. So that'll end up being plus 3 over square root 13 minus z is equal to 2. So that's going to be 4 over root 13 plus 3 over 3 over root 13, which gives me 7 over the square root of 13. I can add the z, I can subtract the 2, and I have this value for my z, which I could write as one single fraction, but I don't have to. Then we'll look at the other case where mu is equal to the positive square root of 13, and we'll get x is negative 2 over root 13, and y is equal to positive 3 over square root 13. And then plugging those into that other boundary equation, we end up with 2 times negative 2 over the square root of 13 minus 3 over the square root of 13 minus z is equal to 2. So a little arithmetic. That's minus 4 minus another 3 would give me negative 7 over the square root of 13. Again, I could add the z and subtract the 2. So minus 2 equals z. Now I have the z coordinates, which means that I actually know the coordinates that I need to test. So from the case where mu was negative square root 13, we got 2 over square root 13, negative 3 over square root 13, and 7 over the square root of 13 minus 2. If I were to plug this into my original equation, the x wouldn't actually matter because there is no x in the original. So we would get 4 times negative 3 over square root 13 minus 2 times all this guy. So 7 over root 13 minus 2. So multiply that, I get negative 12 minus 14. So negative 26 over the square root of 13 plus 4. And if you were to do that thing that you learned about in the 3rd grade where you multiply the top and bottom by square root 13, you'd actually get something that's a little bit nicer to look at because 26 divided by 13 is 2. So this is really just 4 minus 2 times the square root of 13. Okay, now if I do the other point, when mu is equal to positive square root 13, these were our coordinates, negative 2 over root 13, positive 3 over root 13, and negative 7 over the square root of 13 minus 2. And again, x, we're not actually going to use at all. So we're just going to use the y and the z. So we have 4 times 3 over the square root of 13 minus 2 times what we have for z. If I do a little simplifying, 4 times 3, I get 12, plus 14, I get positive 26 over the square root of 13. Then that's going to end up being a plus 4. So I end up getting 4 plus 2 square root 13. Right, and just by looking at this, we shouldn't even need to pull a calculator out to know which one is bigger, right? This is clearly our bigger one because we're adding to 4. Here we're subtracting from 4. So this is going to represent our absolute maximum, and this is going to represent our absolute minimum. And just like that, we have solved an absolute maximum problem that had more than one constraint. Pretty awesome.